Welcome everybody to Reid Construction Systems 2024 series webinar on ReidBar Grout Sleeves CodeMark. My name is Andrew Kamaris and I'm the Technical Development Manager for Reid Construction Systems. Today is an important session for engineers and specifiers, as a ReidBar Grout Sleeve is an innovative coupler style connection used to provide continuity of reinforcement between precast concrete elements for building construction. Our speaker today is Emanuele Narcini. He is a structural engineer who moved to New Zealand in 2015 after 14 years of practice as a professional chartered consultant in Italy. Experienced in structural design, non-destructive testing and structural assessment, in 2016 he joined RAMS at Reid as a project engineer in Auckland. Emanuele is now the Technical Development Engineer for Reid Construction Systems. In 2016, and he is driving technical innovation for Reid and Ramsar products. He also monitors changes and updates of local international relevant standards, reviews internal and external test data against the requirements of the relevant standards, and liaises with third-party laboratories to arrange specific test programs when necessary. Emanuele is also involved with the preparation of technical literature and internal review, and is an active contributor to the New Zealand construction industry. Let's welcome Emanuele as he will now run through the presentation. Also, at the end of the presentation, we will be taking questions. Please feel free to ask your question by typing in the Q&A button in Teams. Thank you. Emanuele?
Kick off with the presentation, and welcome to this first webinar of 2024. As mentioned, we'll be talking about the update in the CodeMark that we had on the ReidBar Grout Sleeve system. So starting quickly, so first of all, we'll introduce a quick introduction on what is the ReidBar Grout Sleeve system, and we'll discuss the main topics that will be the changes in the CodeMark that we had from transitioning from the 2021 to the 2024 edition, and also some insight on the validation testing. First of all, what are ReidBar Grout Sleeves? ReidBar Grout Sleeves, of course, is a full strength splicing solution. It's used to connect precast panels to panels, and also precast panels to foundation slabs. And it allows for the continuity of the reinforcement, and it's a fully tested proprietary construction system for structural connections, and it's certified with a CodeMark for the compliance with the building code. How does that work? There is a ReidBar, which is a 500E grade bar, which is connected in the neck portion of the grout sleeve, and the connection is a threaded connection with a coarse thread, which is the ReidBar thread, and the other bar goes inside the sleeve and it's connected with a grouting. So now let's move on to the next slide. So for these kind of connections in New Zealand, the two main solutions are the drawspec and the grout sleeve to connect these panels to panel connections vertically. And although they do a similar job, that's not exactly the same job. So for the drawspec, we are talking more like a lap splice, in particular a non-contact lap splice. For ReidBar is we can handle that as a mechanical connection, so it's like a mechanical coupler. For drawspec, of course, you have long starter bars that are required for the development length, and there is a requirement for confinement to be able to have a load transfer, and however, the design falls within the scope of 3101, just like a lap splice. For ReidBar Grout Sleeve, we have much shorter starter bars, And the system is self-confined for the load transfer. It's tested like a coupler in free air, so it doesn't need the concrete to transfer the load between the two bars. Although you know, confinement is still a good thing to prevent spalling and cracking. But the load transfer is ensured regardless. And it's a proprietary system, and it's covered by CodeMark certification, as we mentioned before. So for the draw spec, if we look at 3101, when we have these kind of connections, that should be it shall be avoided if possible in ductile regions of the panels. And if it's not possible to avoid, it needs to be staggered. For the grout sleeve, on the other hand, because it's tested as a mechanical splice, and in particular also tested to the close point 8.9.1.3, which is the is referencing ISO 15835, which is the low cycle fatigue test. And so because it's tested against those requirements, it can be used also in a ductile region of a panel without the need for staggering. Now, for the compliance with the building code, for the draw spec, of course, because it falls within the scope of 3101, it's of course follows the path of the acceptable solutions verification methods. So it's deemed to combine through that pathway. For the grout sleeve system, because of the change that happened in 2017 in 3101, and then when it was cited in 2018 by the amendment, the amendment of the building code, what happened is that the cast iron fittings are not anymore within the scope of 3101. Therefore, why we had to go through this pathway of the CodeMark to be able to comply with the New Zealand building code through an alternative solution. But because this is a certified system, it has the advantage of being already checked by the certification body, which is BRANZ, and therefore the building consent authorities must accept the CodeMark certificate as evidence of compliance with the building code, of course, considering that everything has been followed, because it's a strict regime. So let's look at the changes that happened since 2021. And so what you will see here, all these changes are the outcome of us listening to the feedback that we received from multiple sources, from CSOC and specifying engineers, from the contractors, precasters, and also from the independent laboratory that has been testing the system. And so we listen to the feedback, and the outcome of these feedbacks will be those changes that we have implemented. Here we have a quick overview of all the changes, and then we'll deal with this in more detail. So the first change is that now the ReidBar that is screwed again inside the female thread of grout sleeve must be friction cut to guarantee full thread engagement. The procedure to install this bar inside the thread now has an easier procedure for the installation with Epcon C8. So we use Epcon C8, which is an epoxy. We use it as a thread filler, and the procedure has been improved and simplified. Now we have introduced a tolerance range for the embedment depth of the bar inside the sleeve, plus minus 20 mil of tolerance for the starter bar. And we have, alongside PosiFlow, which is still there, we have introduced two more grouts, one from Sika and another one from Fosrock. And lastly, the starter bar that goes inside the sleeve and is grouted now can be any 500D grade default bar. Doesn't need to be ReidBar as it used to be. Of course, it needs to comply with AES NZS 4671. So let's start with the first one. So for the cutting of the ReidBar that is screwed inside the neck. As I mentioned before, here also we'll mention the feedback that we received. This is both coming from the independent laboratory, in this case was Home Solutions, that was testing the system. They had some instances where the bar, because they received the bar crop cut, and they installed the bar that way. And in some instances, there wasn't a full thread engagement, and so you had a thread stripping because it wasn't fully screwed inside the female thread. And also from the CSOC C5 Yellow Book update, the update cites a report where 8 grout sleeves were extracted from an existing building that was designed in 2006, and 2 out of these 8 grout sleeves had insufficient thread engagement. And so we'll link this issue to what happens when the bar is hydraulically cut, cropped. There is a little kink, so the bar is slightly bent at the end, and therefore when the bar is screwed inside the female thread, it gets jammed. There is not full thread engagement. So now with this new procedure that now is, as I said before, this is mandatory. We used to recommend this practice. Now it's actually mandatory to comply with the CodeMark. We need to cut the last bit of the bar. Of course, we're talking about very short length, like 10 mil or something. It's not very long, but it needs to be taken off to prevent this issue. And then we also had this before. We need to mark the thread depth on the bar so that there is a double check on the actual full thread engagement in the system. Now we move on to the application of EPCON C8. Again, the feedback in this case was from the laboratory. And in this case, the procedure that we had wasn't too user-friendly and might have been prone to misinterpretation, and therefore ending with not enough epoxy filling the thread. Therefore, we studied a new application procedure, which is much easier. So we kept the same number of trigger pumps, so the quantity of epoxy is still the same, but the procedure is that we put half of the quantity on the bar in the area that will be marked for the threading, and half inside the female thread on the grout sleeve. The bar is then screwed inside and tightened with a spanner, and that's all. So it's a bit cleaner and easier. Now we move on to the embedment depth. In this case, we had feedback from CSOC, in particular for the task group that was analyzing the grouted connections. And the feedback is that, of course, they were warning engineers that there was lack of embedment length tolerance in the system, which was fair enough. And therefore, we have introduced a plus minus 20 mil of tolerance for that. And so that will be also compliant with the 3109. We move on to the starter bars that in this case we received feedback from the contractors because sometimes the bar that were on site that were not actually ReidBar, they were generic 500D grade bars, the starter bars. This is an issue that particularly happens from the foundation, and therefore would be a very expensive and time-consuming exercise to substitute these bars with post-install ReidBars to be able to comply with the requirements of the CodeMark, which is a prescriptive environment. So we've decided to make the system more versatile And so we have now given the possibility of having any 500 degree E grade deformed bar, not just ReidBar to be used as a starter bar inside the sleeve. And we move on to the grouts. So in this case, the feedback was coming from the contractors, grouting contractors, and some of these have preference or familiarity with other grouts. So alongside, we decided to add, alongside PosiFlow Grout HS, we decided to introduce two more grouts from two popular providers like Fosroc and Sika. So we now have also Fosroc Convextra HS and Sika Grout 212 HP. What these grouts have in common is that these are high-strength grouts. It's difficult to compare apples with apples because, unfortunately, we all tested with different standards, but we are in the ballpark of more than 80 megapascal for the compressive strength of these grouts. Now I would like to cover, to give you some insight on the validation testing and what we considered together with Home Solutions and BRANZ, of course, to validate the system and how to test for these changes that we have introduced. So if we look at, for example, at the 32 mil grout sleeve, we have introduced this new tolerance range for the embedment depth. Therefore, for example, if we look at the 32, now the embedment depth is 300 plus minus 20. Therefore, for the test samples, we ensure that the embedment depth was set to 280. Then we look at the batches of the bars as well that we sourced. So when we sourced the bars for testing, the idea was to try to get stronger bars than average. And this is let's say something that we've been inspired by the ISO 15698, which is doing a similar thing. So we source for, if the long-term quality data from the bar was available, then we could check that the RE, which is the yield strength, for that to be above the mean for the long-term quality. Or if it's not available, to be above 550 megapascal, which is in the middle of the range of the 500D grade bar, which is between 500 and 600. Then we move on to the grouts. And so with these three grouts, we give a tolerance range for the water content for the mixing. And of course, we ensure that we mixed the grout with a maximum water content of the range. I would like also to point out that in one case, we actually exceeded the water content of the manufacturer, which in this case was Sika. This came with a feedback that we had from, again, the testing laboratory. Because what we asked for is not just to test for the strength of the grout, but also to test for the flowability. We wanted to ensure that it was easy to install and to grout. And so the feedback was that when the grout, in this case, Sika 212 HP, was mixed with 3.5 liters, it wasn't as flowable as the other two grouts. Therefore, the consideration was, if that happens on site, what might happen is that people might add more water. And so we agreed on to increase the water content to 4 liters and test it that way. And the test was successful. So that's why you will find here that you have a higher water content. Then we move on to the marking area. So this is, so when we're discussing with BRANZ to include other 500E grade deformed bars in the system, the initial consideration and pushback from BRANZ was that the deformations of ReidBar are more prominent compared to the deformations of the other bars. And so specifically, it's called the specific projected Reid area. And so the consideration was to, okay, let's look at the other bars in the market and let's see how what their specific projected Reid area is. And so we had a look at that, and between all the other bars in the market was pretty similar. It was actually a little bit less than ReidBar. And also we noticed that for the bars manufactured by Pacific Steel, coincidentally, which is the same manufacturer of ReidBar, the marking of the 500 grade bars is missing. The marking area is missing a couple of ribs. So what we did, we agreed on testing this, which is the smoothest portion of the bar inside the sleeve. So we included this area inside the sleeve. And therefore, with all these, we ensured that we were testing the worst case scenario for the elongation at 0.7 FY for the low cycle fatigue, and also to demonstrate the mode of failure of the mechanical splice, where we want to achieve the ductile failure of the bar, clear of the coupler. Now, there is another requirement which is unique to New Zealand, and is to the capacity of this coupling system to develop the upper bound breaking strength of the bar. So when we look at the reinforcement bar, the behavior that is required by AS NZS 4671 for a 500 E grade is that the lower characteristic yield strength needs to be above 500 megapascal, and the upper characteristic yield strength below 600 megapascal. And also that the ratio between the ultimate capacity and the yield needs to be between 1.15 and 1.4. Therefore, if we multiply with the yield, we get that the ultimate in theory could be between 575 and 840. This is the full range. But then we look at the definition of the upper bound breaking strength from 3101. So if we don't have an appropriate study conducted on these bars, we can consider as upper bound breaking strength 1.25 times the upper characteristic yield strength, which is 600 for a 500 E grade. Therefore, we have 750 megapascal. And so then if we look at what is actually really produced by Pacific Steel, for example, we can see that the upper characteristic ultimate strength never goes beyond 725 megapascal. And so how do we test for this performance, and how do we get the bar? So even if we want to source a bar that is 720 something megapascal, this only happens once every few years. It's not something that happens every day. So it's not that easy and practical. Not to talk about 750 MPa, which is never the case. So how do we do it? And the trick that we have adopted is to cook the bars. So we heat treat the bars. This allows us to bring the bar to an ultimate strength that is can be anywhere between 800 megapascal and 1100 megapascal. It's not very consistent, but it's consistently above the threshold of the 750. So it does the job. And just to give you an example, just some random results that we had. In this case, for example, we still didn't manage to break the fitting. So the idea with this test is to try to break the grout sleeve or to pull out the bar, not to have the, not to break the bar, but it still happens. In this case, for example, was at 838 megapascal of stress on the bar, which is 112% of the upper bound breaking strength, so all good. And in this case, we managed to break the grout sleeve, and it happened at a stress in the bar of 1086 megapascal, which is 145% of the upper bar breaking strength, which is well above what's required. So happy days. Another topic that I would like to cover is the brittle fracture resistance. So this is actually the clause that drove us to reach out for a CodeMark, specifically the last clause, which is the prescriptive requirement of anchors not being manufactured from cast iron. And the same applies to couplers through clause 8.6.5.2a. And the other thing is that aside from this prescriptive requirement, there are requirements of testing to prove that these systems possess resistance to brittle fracture at surface temperature, which they are intended for use. In particular, the concern might be low temperature. The problem is that 3101 doesn't give guidance of what is an appropriate test method, not even in the commentary, and also AS 3600 or even international standards like ISO 15835, which is a standard for testing the couplers, also cited by 3101, and ISO 15698, which is a standard for testing of headed anchors of reinforcement bars, which is cited by the bridge manual. They don't actually cover the testing against brittle fracture resistance of the couplers or fittings. So the point here is that if we accept to check just the material and not the mechanical splice as a whole, which would be more interesting, then the NZTA bridge manual advised to perform the Sharpie V-notch impact test at 0 degrees. How it works is that a little sample is cut out from the coupler when it's possible. Of course, it depends on how big is the coupler. If the coupler is small, that might be very difficult. The standard measure of the sample is 10 by 10 by 55. And then there is a little incision that is cut in the middle, and then this element is frozen to 0 degrees, and there is this pendulum that strikes the sample, and depending on how resilient the sample is, it absorbs energy from the impact, and so the pendulum doesn't swing high too much after the impact. And the thing is that this is a test. First of all, it's a test on the material, not on the actual element, and also not on the actual connection. So we don't know what happens inside the threads and all the rest, particularly when there is a system that, which is not the case for our system, but when the thread needs to be cut from the bar with some cold forging or something like that, that might compromise the ductility. And so this is a test which is suitable for steel, but is not actually fit for purpose for spheroidal graphite iron because of its nodular composition. So how we handle this is that we consider that the fittings like grout sleeve are made from spheroidal graphite iron grade 603, and Reid brace components, they're also manufactured by Ramset now, Ramset Reid. Reid brace are made of the same material, exactly the same grade. And this system, the Reid brace system, was extensively tested by the University of Auckland in 2018. It was subject to static and dynamic testing, and also to impact loading at freezing temperature of the components. And the outcome of these tests was that the minimum in-service temperature for the system would be suitable as -5 degrees Celsius. This is, of course, if we are fine just checking the material. The ideal thing would be, if we can go above and beyond, to test the whole thing. And so that's why we reached out to Des Bull, and together we came up with a possible test procedure, and we presented that at the Concrete Conference last year. And so watch this space for future. And then just to recap, what are the changes that we have introduced with this new CodeMark in 2024? So now we have the ReidBar that goes inside the threaded end of grout sleeve must be friction cut. That we have changed the application procedure of EPCON C8, which is now easier. And we have introduced a tolerance for the embedment depth of the starter bar with plus minus 20 millimeters. And the starter bar can now be any 500E grade deformed bar, of course, compliant with AS NZS 4671. And now we have 3 high-strength grouts available for the system. Of course, Ramset Posiflow HS, Sika Grout 212 HP, and Fosrock Grout Convextra HS. And so now I'll open the floor for questions. Thank you very much.
Excellent presentation. Yes, now we're open for questions, so please feel free to ask questions. I've got some coming here. So one question, Emmanuel, is does Reid have a structural specification draft for grout sleeve which can directly be used in project specifications?
Yes. So if you visit our website, all these changes that we presented, they're all, we have a specification guideline that supersedes the old one.
Excellent. Okay, next question is, the ReidBar is just normal HD 500 bar as reinforcing bar. Where can we buy ReidBar?
ReidBar is from the Reid distributor. So the ReidBar is actually made by Pacific Steel, and it's distributed with the reinforcement distributors in New Zealand. So it's made in New Zealand and distributed in New Zealand by, I'm not sure which are the dealers, the distributors, but yeah, the one that sell the bars from Pacific Steel.
Okay. Another question is, can the bar coupler be used to splice the connection if the starter bar is ReidBar?
So hold on.
Can the bar coupler be used to splice the connection if the starter bar is ReidBar?
If the starter bar is ReidBar, of course, a coupler can be used instead of, were we talking instead of grout sleeve? If that's the, I'm not sure about the question. Of course, now within the as an alternative to grout sleeve, but it's not really an alternative because the application would be different. We have the steel coupler, the ReidBar steel coupler, which is a full strength coupler, which is also been tested to all the requirements of 3101 and of the NZTA bridge manual. And yeah, definitely a coupler can be used instead of grout sleeve, but it's a bit different application because the grout sleeve is generally it's used inside a precast element, so that's why the applications might be different. Yeah.
Okay, we've got another one here just now. It says, does the detail work well with insulated precast sandwich panels to footing connections?
Insulated?
Yeah, insulated precast sandwich panels. Does the detail work well with insulated precast sandwich panels to footing connections? I'm assuming that with an insulated precast sandwich panel, that the structural section of the insulation part has got enough thickness to accommodate for a grout.
Yeah, for the system, yes. Yeah,
Yeah.
if that's the case, because the grout sleeve is has a certain diameter,
Yeah.
and so if it fits, yes, but it needs to be able to fit inside
Yeah.
the layer, yes.
For example, if it was a 150 thick structural, then you had the insulation perhaps maybe 30 or 50 mil, then the fascia, that would work.
Yes, yeah, that would work,
Yeah.
yes.
There's another question, was set for a couple of minutes ago. Is the paper presented at the conference with theirs available to read?
Oh, yes.
Hmm.
I'm not sure if you send me an email or reach out to me, we definitely can send you the paper.
Yeah. Another question. Will Reid provide friction cut bars or will it be responsibility of the contractor?
Yeah, it would be a responsibility of the contractor. As I mentioned before, we actually don't manufacture the bars, and we don't do the bars. Those are handled directly by Pacific Steel and then by the distributors of Pacific Steel.
Just another question. Great, keep them coming. How is the coupler grouted? What equipment is required?
Yes, so for the grouting, it depends on the contractor and how they generally have like a pump and a little mixing station for the pump to be able to grout, and so the batches are small, so they go with the mixing by bag, so bag by bag. So they mix it on the spot, and then they follow the procedure of mixing, and then they start grouting from the pumping from the bottom hole of the grout sleeve. I didn't cover too much the installation procedure in this presentation because I was more focused on the changes of the CodeMark, but we have a detailed installation procedure as well that can be downloaded from the website, and you will see that the operations are consequential, so that there is of course the panel that needs to be put on top of the other panel with the shims, and then there is the dry packing, and then there is the joint sealing, and then after the joint sealing, the grouting of the grout sleeves one by one.
Yep. Got another question. Can the grout sleeves used in a ductile design? Can the grout sleeve?
Yes. So if it's a panel, yes. So that's the consideration that I showed. I don't remember what number the slide was, but definitely that's from 3101, because the system has been tested against the requirement of the ISO 15835 low cycle fatigue. It can be used in an area where ductility is required in the panel, and it doesn't need to be staggered.
I don't know if this is a question or a statement, but there's something about reinforcing distributors. I think there was a question about where can we get ReidBar, and maybe just reinforcing distributors, and there's some statement regarding what that is.
Yeah.
How suitable would the system be at the base of PC columns in portal frame buildings? Yeah.
Yes. So the difference is that compared to what I mentioned before, if we look at columns instead of walls, it's a little bit different. So for the ductility application, that's a different thing. So if you look at 3101, mechanical couplers shouldn't be placed in highly inducted regions of columns where it's high inelastic demand is expected. So what I commented before doesn't apply, but it can be done, but not in areas where you're expecting highly inelastic demand.
On behalf of everyone, I think we'd like to thank Emanuele for his very informative presentation on the ReidBar Grout Sleeve CodeMark. So watch this space. There'll be another series of webinar for Reid, and the topic will be coming up soon. Yeah, we really thank you. And then just before we go, someone asked about one more thing. So what ductility? So it's a question, and I suppose it is. So what ductility is the question?
I mean,
But up to,
the restriction is exactly the same of a mechanical coupler in 3101. So the same principle that you would apply with a mechanical coupler.
yep. On behalf this failure is outside the zone of the coupler, the bar yields and breaks and so on and so forth. So
Yes.
that's the answer to that question. That's the ductility of the bar. Okay, all right, I think that's it. So thank you very much, everyone, for your attendance. Until next time, and enjoy the rest of your day. Thank you all.
Thank you. Bye.
Bye-bye.